Welcome to the next session, my dear friends. So we are discussing about the permanent hardness removal using lime soda method in the previous session. The same thing we are continuing in this session and after lime soda method we will discuss the rest of the two methods to conclude this chapter. Okay, so let us discuss them. Now, here when coagulation and lime soda process are combined, I told you in the previous session, so the dosage of the lime, the dosage of alum can be reduced when we are using this along with the alum, because lime is also acting like a alum, and so the residual hardness that will be left in lime soda process about 50 mg per liter, that means 40 mg per liter in the form of CaCO3 and 10 mg per liter in the form of MgOH twice, that will be left over inside the water as a residual hardness. So complete hardness is not possible in case of lime soda process. And how much lime is needed for removing hardness? So doses of lime, doses of lime needed, lime as CaO needed is equal to lime as CaO. How much lime is needed as CaO is equal to 56 by 100 into total hardness. So if you know the total hardness, then the lime requirement is equal to 0.56 times of total hardness. 0.56 times of total hardness. Okay, total hardness in mg per liter as CaCO3. Okay, mg per liter as CaCO3. Similarly, what is the total dosage of soda ash, Na2CO3, sodium carbonate? Dosage of soda ash required. Dosage of soda ash, that is Na2CO3 needed, is equal to, so the molecular weight of this is 106. The molecular weight of soda ash is 106. So 106 by 100 multiplied with total hardness, or we can call it as 1.06 times of the total hardness in mg per liter as CaCO3. So this is the dosage of soda ash needed. Okay, when concentration is given in milli equivalent, when these concentrations instead of milligram per liter, it was given in milli equivalents. Okay, when the concentration is given in, when the concentrations are given in milli equivalent per liter, then hydrated lime, the requirement of the hydrated lime. So requirement of hydrated lime, that is CaOH twice, is equal to the present of concentration of CO2 plus HCO3 plus magnesium. So what is the concentration of CO2, HCO3 and magnesium? If you look back the reactions, so here what is the HCO3 concentration? Okay, that HCO3 concentration is removed by the lime and CO2 is removed by lime. Okay, hydrated lime, that is CaOH twice. CO2 is removed by lime, HCO3 is removed by lime, and magnesium is also removed by lime. So the total concentration is equal to sum of the concentrations of these three. And soda ash required, soda ash required is equal to calcium plus magnesium, total concentration of calcium plus magnesium minus CO3 HCO3 plus OH minus CO3 plus HCO3 plus OH minus concentrations. So these three will be taken care by lime. So that is why in soda ash, apart from this, whatever the hardness is present, that will be taken care by soda ash. So these are the requirements of lime and soda ash when the concentrations are given in milli equivalent. So this is in mg per liter. So very important. It is very important. Okay. So next method we are moving on, that is base exchange process or ion exchange process. Base exchange. Next method is base exchange process or ion exchange process. Base exchange or ion exchange. So base exchange or ion exchange process Okay. So let us see what is this method. See, in this method, so in this process, the name itself says ion exchange. We are exchanging the ions. What ions we need to exchange? I already discussed this same kind of thing in removal of salinity. Okay, in salinity we discussed this. Ion exchange means there we will exchange the ions. Okay, we will exchange the ions. Here this is cation exchange process. Ca2 plus and Mg2 plus ions which are responsible for hardness are exchanged. Okay, or exchanged. So that is why we call this method is also called as cation exchange method. So it is also called as cation exchange process. It is also called as cation exchange process. Cation exchange process. We also call this as cation exchange process, in which we exchange the cations. How we do this? So there will be a bed called zeolite bed. So there will be a bed called zeolite bed. This is called zeolite bed. So this zeolite bed will be having a lot of sodium ions in it. So it will be having lot of sodium ions in it. So the zeolite bed will be having some kind of cations. Predominantly it is sodium cations will be present, and these sodium cations, okay, so these sodium cations will replace the calcium and magnesium cations present in the hard water. Okay. Zeolite. What is zeolite? Zeolite. So zeolite is a natural or synthetic cation exchange material made of silicates of sodium and aluminum. So it is a natural or artificial cation exchanger made up of silica of sodium and aluminum. Sodium and aluminium or alumina. Sodium and aluminium. So the formula of this is, it is also called, this zeolite is also called green sand. This is also called green sand. Zeolite is also called green sand, and the formula of this zeolite is Na2O. This zeolite formula is Na2O Al2O3 XSiO2. So the formula of zeolite is Na2O Al2O3 XSiO2 and YH2O. Okay, YH2O. So here, whatever the compound which is present here, so this let us take this as Z. So now I can write this as NaZ. Okay, we can write this as NaZ. So this NaZ, okay, this NaZ when reacts with calcium or magnesium's permanent hardness causing compound, that is 2Cl minus, SO4 2 minus and 2NO3 minus, any of the material, or HCO3 minus. Okay, so any material which is present in the form of calcium and magnesium. So here this cations will be replaced by this sodium and it forms Na. It forms a compounds of sodium 2Cl minus, SO4 2 minus, 2NO3 minus and HCO3 minus plus CaZ or MgZ. So this Na2 will be replaced by the calcium and magnesium, and at some time or other this process is completely taking place. Okay, this process is completely taking place. So at some point or other, all the sodium ions present here, will be completely replaced with calcium and magnesium. So while we send calcium and magnesium through water into this zeolite, so we are getting out the sodium plus ions. We are bringing these sodium ions out of this zeolite bed and refilling this zeolite bed completely with calcium and magnesium ions. At some point of time or other, so the water coming out of the zeolite bed may not be treated. That means zeolite is completely exhausted. In that condition, we have to regenerate the zeolite again. Okay, so we have to regenerate the zeolite again when the zeolite is completely exhausted. When the zeolite is completely exhausted by calcium and magnesium ions. Okay, magnesium ions magnesium ions, it will be regenerated. It will be regenerated by concentrated NaCl solution, by concentrated NaCl solution, by sending concentrated NaCl solution, which is also called brine solution, which is also called brine solution. So this brine solution we will use to regenerate. This brine solution we will use to regenerate the zeolite bed. Again, we will refill the zeolite bed with sodium ions by sending concentrated salt solution, concentrated salt solution. So here the water which is coming out of this zeolite bed, okay, so the water which is coming out of the zeolite bed will have zero hardness. The water coming out of a zeolite bed will have zero hardness, will have zero hardness. So zeolite, using this method, using this zeolite method, we can achieve zero hardness. Using this zeolite method we can achieve this zero hardness, whereas we cannot achieve it using the lime soda process that we can achieve here. So because as it is zero hardness, okay, as it is zero hardness, so the water which is going out through the distribution system, which is coming out of this ion exchange method, will not harm, will not cause any problem to the pipe network, to the distribution network, as the hardness is very less. So there won't be any problem of incrustation in the pipe. But when the turbidity is very high, okay, so when the incoming hard water which is having more turbidity, for those kind of turbid waters, so this method is not suitable, because the turbidity will choke the zeolite. So will choke the zeolite and does not make the water to flow through this zeolite bed. So that is why for turbid waters we cannot use this method. And also if it is highly hard, if it is very hard water, then again zeolite will get exhausted very early. So that is why what we do generally is we will do lime soda process to bring that hardness to a considerably a lesser value. If the hardness is very high, then what we will do, first we will send it into the lime soda method. From lime soda method we reduce the hardness to some extent, and then we will go for zeolite method where we need very less hardness. So if you are sending this water to boilers and all, in those cases hardness is very important. So in those cases what we do generally, we prefer zeolite. Okay, we prefer zeolite. And if it is for drinking water, generally lime soda method is enough, because a 50 mg per liter of hardness is not a problem for us, because as per IS 10500 we can take up to 200 mg per liter of hardness is allowable for drinking water. So 40 mg or 50 mg per liter is not a big problem. And here in this problem, in this method, okay, in this method, NaHCO3 which is coming out of the zeolite, coming out of the zeolite bed will cause foaming. So NaHCO3, this causes foaming will cause foaming inside the boilers. inside the boilers. Inside the boilers because of the presence of the NaHCO3. Okay, and also this is not suitable for turbid waters. This is not suitable for highly turbid waters, as well as and when the concentration of hardness is very high. And the concentration of hardness is very high. Okay, so that is why this method we don't prefer much, and where we need zero removal of hardness, there we need to prefer this method. And this method is also having another drawback, that is it is very costlier method. Okay, it is very costlier method because especially when the water contains iron and manganese ions. When the water contains iron and manganese ions. They react with zeolite and forms strong bond which cannot be broken, and makes zeolite unfit for exchange of ion. So when it cannot exchange ion, then that zeolite is of no use. When it is sodium ion present in the bond of zeolite, so then sodium can be easily removed by calcium, and calcium can be easily removed by sodium depending upon the concentrations. But if it is reacted with iron and manganese, then the zeolite bed will form a strong bond with iron and manganese, and it won't allow any more ion exchange. That means that portion of zeolite is of no use. So that is why when water is containing color causing compounds like iron and manganese, so then the zeolite will gets damaged quickly and makes this method uneconomical. Okay, makes this method uneconomical. Next is design of ion exchanger. So what is the volume of ion exchanger that is needed? What is the volume of ion exchanger that is needed? Let us see. Design of the ion exchanger. Design of ion exchanger. See, here design means volume of ion exchanger, determining the volume of ion exchanger. Volume of ion exchanger. Volume of ion exchanger is equal to Q. What is the incoming water? So what is the incoming water, that is in mld? Okay, what is the discharge? Okay, what is the discharge, and what is the total hardness. What is the total hardness inside this discharge? What is the total hardness in mg per liter? What is the total hardness in the water in mg per liter divided with capacity of ion exchanger? Capacity of ion exchanger. Capacity of ion exchanger in kg per meter cube per day. Kg per meter cube per day. So we need to bring them into uniform units. I am taking the just unit like that. So we need to convert this milligram into kg. So uniformity needs to be maintained. So Q into total hardness by capacity of the ion exchanger. So generally the capacity of ion exchanger, ion exchanger varies in between 0.20 to 100. Okay, generally the capacity of ion exchanger varies in between 20 to 100 kg per meter cube per day. Kg per meter cube per day, general value. So they will give you the value of ion exchanger, okay, in the examination. And the rate of flow, generally the rate of flow is kept in between 0.2 to 0.5 meter cube per minute per meter square. The rate of flow is kept in between 0.2 to 0.5 meter cube per minute per meter square. So this is the rate of flow generally we maintain in the ion exchanger. And the cross-sectional area of ion exchanger that is equal to pi d square by 4, where d is the diameter of the ion exchanger, is equal to the q, whatever the q we are having, q by this rate of flow. So q by v, that is nothing but the surface area. Q by v, that is rate of flow. Q by the rate of flow. This is, let us take this as v. So that is discharge upon a rate of flow. Discharge upon rate of flow. So then you will get the area, cross-sectional area, and from this formula we can also find the diameter of the cross-sectional area. So likewise we do the ion exchange method. So next method is demineralization. This is the last method of removal of hardness. Demineralization. Okay, so in this method, this process removes minerals in water. Okay, so here there are two processes is involved in this. One is the complete removal is by first passing the water through the cation exchange resins and then through the anion exchange resin. So demineralization, so this method involves two stages by which we remove the minerals. We remove the minerals causing hardness. Okay, minerals causing the hardness. So first stage in the first stage, what we do, we remove the, we send the water through cation exchange. So in the first stage, so whatever the cations, Ca, HCO3, CaCl2, Ca, HCO3, CaCl2, Mg, HCO3 and MgSO4. So all those things, okay, so all those things, and and 2NaCl plus 2NaCl plus H2R. This is the cation exchange resin. So this is cation exchange resin. So H2R is nothing but the cation exchange resin. Here, so these minerals, whatever the minerals present in this water, okay, either they may be causing hardness or they may not be causing hardness. Demineralization method will remove all the minerals present in the water. Will remove all the minerals present in the water. So this is called cation exchange resin. This is called cation exchange resin. Okay. So this cation exchange resin will remove all the minerals present in the water. So all the cations present in the minerals will be removed. So the cations in the minerals means if you take these reactions, calcium, magnesium and sodium are the cations. So they will be removed like this. So CaR, okay, plus this, if you take CaHCO3, CaR plus 2H2O plus 2CO2, 2H2O plus 2CO2, and if you take this one, so this is CaR plus 2HCl. If you take this MgR plus 2CO2 plus MgR plus H2SO4, MgR plus H2SO4, and here NaR, 2NaR plus HCl, 2HCl. Okay. So likewise, the resin, the cation exchange resin will completely exchange the cations. These are the cations are being removed. So this is the first stage of removal. So this is first stage. Okay. So this is the first stage. So then in the second stage, we will send this water for anion exchanges. We will send this water into the second stage, that is anion exchange. So anion exchange means, say if there is any anion in the form of HCl, so whatever the anions, HCl plus ROH. So this is anion exchange resin. This is anion exchange resin. This is anion exchange resin. And this anion exchange resin will remove the anions like Cl minus, and it forms H2O plus RCl. It forms H2O plus RCl. So this is exhausted cation resin. If completely the resin is taken by calcium, resin is taken by magnesium, resin is taken by sodium at some point of time or other, so this resin will completely exhausted. So once the resin is reacted with calcium, reacted with magnesium, reacted with sodium, means this is exhausted cation resin. So this is exhausted anion resin. Exhausted anion resin. Okay, this is second stage. This is actually anion exchange is second stage. So once these resins are exhausted completely, we need to regenerate them again. We need to regenerate them again in order to use this method. So this exhausted cation exchange resins can be regenerated by treating it with HCl. So these exhausted cation resins, whatever the exhausted cation resins, so this CaR or else we write it somewhere here. So the exhausted cation resins Ca, Mg and sodium are plus HCl. So we will use HCl in order to regenerate the cation exchange resin. Then it will be regenerated like this. So H2R and Ca, Mg, Na, Cl2. So we can form this. Now what we do here is, once the water is going out of the chamber, okay, once the pure water, treated water left the chamber, then we will add this impurity HCl again to the residue. We will add this HCl to the residue. So in this, when we are adding this HCl, there won't be any water left in the demineralization chamber. So all the water, treated water is taken out, and whatever be the leftover water, in that we will add this in order to regenerate the resin again, in order to regenerate the cation exchange resin again. Similarly, anion exchange resin is also regenerated by sodium carbonate. So anion exchange resin, that is RCl, is added with Na2CO3, then it will form ROH, okay, plus 2NaCl. It will form ROH plus 2NaCl, H2O plus CO2. So this is not a complete reaction. Actually there will be something here on the reactant side. So that is not necessary. The only thing which is necessary is the resin. This is the anion exchange generator. So this is the anion exchange generator. So to regenerate the anion exchange resin, we have to add sodium carbonate to regenerate. This is important for exam. To regenerate anion exchange resin, we add Na2CO3. That is important. So the reactants and all are not important here, and what are the reactants and what are the products are not important. What is the main reactant which we use to generate this anion exchange resin, that is important, that is sodium carbonate. And to generate the cation exchange resin, we add HCl. So these things are very, very important. And using this demineralization technique, we can create any kind of hardness, any set of hardness ranging from 0 to any value we can maintain. That means using demineralization method, the hardness can be removed to any extent from 0. Okay. From demineralization technique, hardness can be maintained, hardness can be reduced to any value, to any desired value, up to 0, hardness, So that is the importance, that is the beauty of demineralization technique. From this technique we can create any kind of hardness of the water. Okay, so these are all the miscellaneous water treatments which we perform for water other than the conventional treatment. So we have discussed almost, we have completed the water supply engineering. Only 1 or 2 topics are left in water supply, that is water distribution and also well hydraulics, which is left over. We have discussed all the important thing for the examination, and now in the next session we are going to solve all the previous GATE questions from 1991 to 2020. All the questions we will discuss. Okay, thank you so much.